As your assignment for this week says, it is time for a major review of force and motion. Let's take a look. What are forces? Inertia, gravity, and Newton's laws. Let's start with forces. What is a force? Remember, a force is a push or a pull. It may be unbalanced or it may be balanced. If the force is unbalanced, then the object will move. But if the forces acting on the object are balanced, then the object will not move. What does a force do? A force can give energy to an object. It can make an object move. It can make an object stop. Or it can change the direction of the motion of the object. In the case of the animation, you see that gravity is making the different colored objects move in different ways. Forces are vectors represented with arrows. Remember, a vector is something that has direction and magnitude. In this thing, you see the friction between the table and the book exerts a leftward force upon the rightward moving book. The table pushes upwards on the book, and gravity pulls downwards on the book. Friction would be going opposite the motion of the book if the book is going toward the right. Unbalanced forces change the motion of an object. For example, when the truck hits the car, there is an unbalanced force on the ladder causing it to continue moving, even though the truck and the car have both stopped. The truck motion is changed when it hits the car, but again, the ladder keeps going. Unbalanced forces can change motion in other ways too. For example, if there is an unbalanced force on the tail of the plane going in the same direction as the plane speeds up. But if the green arrow representing the wind in the second picture is going against the plane, then the plane slows down. And finally, if the green arrow is going at an angle to the plane, it causes the plane to drift sideways or change direction. Forces are added with vectors. If the boat is going with the current, then it's going to drift sideways as the current pushes it. If the boat is going without a current, then it can travel in a straight line. The current in this case would be going toward the top of your screen. Now let's talk about friction. Friction is a force which opposes motion, bringing objects to rest. To oppose motion means to go against it. It means it's making things stop or slow down. There are three types of friction: rolling friction, sliding friction, and fluid friction. Now let's talk about inertia. Remember that inertia is the tendency of an object to stay at rest or in motion, meaning to continue doing whatever it's doing. Objects that have greater mass also have greater inertia. That means if a very heavy object is standing still, it's going to be really hard to make it move. Or if a very light object is standing still, it's going to be really easy to make it move. Picture the elephant and the mouse. The elephant has more inertia, but they fall at the same rate. Why is that? We'll get to that in a moment. Inertia would keep astronauts in motion in space because there's no friction to slow them down. So as the two astronauts collide, the one pushes the other. Seatbelts in a car protect against inertia. This man wasn't wearing his seatbelt, so when the car hit the wall, he flew out of the car. If he was wearing his seatbelt, that would have stopped him. But since he wasn't, he was in motion and he wanted to continue being in motion. Lastly, let's talk about gravity. Gravity is the attractive force between all objects in the universe. Everything that has mass has gravity. The more mass an object has, the greater its gravity. The more distance between the two objects means less gravity. Massive objects have lots of gravity. Tweety Bird is not a massive object. Its gravitational attraction is small no matter what the distance. Here's a picture of the gravity of Earth acting on the student and the force of the student on the Earth. The Earth exerts a force on the student, and the student exerts a force on the Earth because of gravity. Which is the greater force, however? Well, the greater force is the force applied by the Earth because it's so much more massive than the student. Now let's review Newton's laws. The first law is the law of inertia. The second law is stated as force equals mass times acceleration. And his third law said that there is an action and reaction force. Newton's first law. Remember, I did something like this in one of the videos that I showed you. Newton's first law is the law of inertia. It states an object at rest stays at rest, or an object in motion stays in motion unless acted on by an external, unbalanced force. So, here we have the astronauts again. The first astronaut is going to continue staying still until he's acted on by the force of the second astronaut. Those two astronauts are going to stay in motion until they're acted on by a third force that would make them stop. Inertia is what keeps satellites in orbit. Inertia also keeps you at rest when your parents tell you to clean your room. Not really, that's just a funny joke. Newton's second law says that force equals mass times acceleration. A force is needed for acceleration to happen. Acceleration will occur in the direction of the force. Which cars are accelerating? If you watch carefully, the green and the blue cars are accelerating. The red car is traveling at a constant speed or velocity. The blue car and the green car both speed up, but the blue car is accelerating more than the green car. A force is needed for acceleration. Will these accelerate? A skier going downhill. What force is acting on the skier? Will the skier going downhill accelerate? Well, yes, because gravity is acting on the skier, causing him to speed up. How about an astronaut on a spacewalk? Would an astronaut accelerate? Are there any forces acting on the astronaut? Well, we know there's no gravity in outer space. We also know that there's no or very little friction because there are no air molecules to slow him down. So, could an astronaut on a spacewalk accelerate or speed up, slow down, or change direction? Only if there was an outside force acting on that astronaut. Which of the following will accelerate? In this video, what you're seeing is an astronaut from the United States on the moon, and to demonstrate the law of gravity, he is dropping a hammer on this side and a feather on the other side. Notice that without air resistance, they both hit the moon at the same time. Will a bullet shot from a gun accelerate? What forces are acting on that bullet? Well, if you think about it, a bullet is eventually going to come back down because it's being pulled down to the earth by gravity. It's also experiencing friction from air resistance as it travels through the air. So will it accelerate? Yes, it's going to slow down and eventually stop because of the forces acting on it. A hammer and a feather dropped on the moon, are they both going to accelerate? Yes, because there is gravity on the moon. So they do speed up as they fall, but since there is no air resistance to make their speeds different, they both land at the same time. Remember Newton's second law, it says that force equals mass times acceleration. Force is measured in the unit newtons. A newton is equal to 1 kilogram going at an acceleration of 1 meter per second squared. For example, a car with a mass of 1,000 kilograms hits a tree and decelerates at 50 meters per second per second. What force does it exert on the tree? Well, mass times acceleration equals force. So 1,000 times 50 is 50,000 newtons. That's a lot of newtons. If a car is traveling at a constant speed, is any force acting on it? Although there are no forces acting on the car, gravity, friction, and air resistance, although there are forces acting on the car, like gravity, friction, and air resistance, there is no acceleration. That means the forces must all balance out and therefore equal zero. Gravity is a force that causes acceleration. On Earth, all objects accelerate at 9.8 meters per second squared if you ignore air resistance because of gravity. Remember to think about acceleration like an interval. That means every second that goes by, the object's speed increases by almost 10 meters per second. That's going really fast. No matter what the mass of the object, all objects on Earth accelerate at 9.8 meters per second squared. Both the elephant and the feather, or in this case the penny, land at the same time. If you have free fall with air resistance, the penny takes longer to hit the ground. And finally, let's look at Newton's third law, which says for every action there's an equal and opposite reaction. If you look at the man jumping off the boat, when he pushes backwards on the boat, he moves forward and the boat moves backwards. Action and reaction forces occur in pairs. Those pairs have to happen at exactly the same time. If they didn't, when you put your hand down on the table, your hand would go straight through the table if the table didn't push back on your hand. For every action, there's an equal and opposite reaction. For example, in rocketry, the gases pushing down is the action force. They come out of the back of the rocket. The ground pushing back on the rocket is the reaction force. And the rocket propelling forward or up is the effect. Here's another example of Newton's third law. When the boy pushes the girl in the back, the girl accelerates to the right, and the boy accelerates to the left. However, if the boy tries to push on the elephant accelerates to the right, but its acceleration is very small because its mass is so much greater than the boy's. How do Newton's laws describe the motorcycle and the rider? Well, it's first law. Newton's first law says that inertia keeps the rider moving forward. The first law says that objects in motion remain in motion unless acted on by an unbalanced force. So the rider keeps going even after the motorcycle is stopped because there's nothing to stop the rider. Newton's second law says the force with which the rider hits the ground will be equal to his mass times his acceleration. So if he had more mass, he would hit the ground with more force. And the third law says the bike pushes the wall and the wall pushes back on the bike with equal and opposite force. In this case, causing damage to the front of the bike. We have reached the end of our force and motion review. Hopefully you use this to study for your unit test.